Hello, and welcome to everyone who wants to know what normal distributions are and how to use them, at least in terms of the empirical rule, which is generally the first thing we do with normal distributions, the most basic thing we do. And so something that we learn about very often in geometry or algebra 2, maybe algebra 1. Before we get into, this is not really something, you might start the year in AP Stat with it, but you'll go pretty far beyond what we're doing here today in AP Stat. So let's just talk about real quick why I need to know this. What kind of problems will ask me to have this knowledge? How do I, what will I have to understand? So let's look at this problem, excuse me. It says, number one, the high temperature in Chicago for the month of August is normally distributed with mean 80 degrees Fahrenheit and standard deviation of 8 degrees. And then it asks me a bunch of questions about how many days in August are going to have a high temperature above 96, what percent of days have a high temperature below 72, what about between 64 and 88. So it's just asking me a variety of questions about how the temperatures are supposed to work in August in Chicago. And the key thing it tells me here is that they are normally distributed. It's when you see those two words in a problem that we are dealing with this, and that you know that you can use some of the knowledge you're going to get right here, right now. So now what does it mean to be normally distributed? Basically what it means is that your data fits what we call a bell curve or a bell-shaped curve. And what that means is this part right here, this is the mean. And a lot of times we use mu for the mean. Usually we use mu for the mean of a whole population. And if we use X bar, we're talking about just a sample. We're not going to get into the difference here, but we're just going to assume that we're talking about all of the data. Okay? So mu is my mean. All right? So the mean is the middle. If we look at this, basically this is indicating to me that most of the data, like you could think of it as having dots of data all throughout here, most of my data is around the middle. This part of the curve and this part of the curve right up in here, this is the biggest part of what's underneath the curve. So it's mostly right there around the mean. If I go far away from the mean, there's not much there. There's not much here. So something that is normally distributed is mostly, you're going to have most of your data close to the mean and less of your data farther away from the mean. Another thing that happens is, and by the way, this is the mean. Well, we'll come into that. Let me come back to that. Getting ahead of myself. The other thing is, notice how symmetrical it is. The two sides mirror each other exactly. That's another thing we mean by being normally distributed. Now, because of the symmetry, because they're symmetrical, this would actually be the median also. Okay, but and it would also probably be the mode. But really, we usually only talk about the mean in this context. Okay, so the middle of your normal distribution curve or your normal curve is where the mean is. Now, when we talk about most of the area, well, most of the points, most of the data seems in the middle here. I just use the key word, area. It's really the area up underneath the curve that tells me what's going on here. In other words, the most area up under the curve, the most space under the curve is right here near the middle. That means most of my data is going to be right there near the middle. The smallest areas up under the curve are out here to the edge. So that means not very much of my data is going to be out there near the edge. Now, when we talked about statistical basics, where we put in, very often we use a graphing calculator, we put in our data and we put it in a list, and then we get the one variable stats. So we talk about the 5 special numbers, the minimum, the Q1, the median, the Q3, and the max. But the other two things we also tend to talk about are, and here we used X bar for mean. We talk about the mean. And we talk about the standard deviation. Now, this is another case where there are two different ways of looking at the standard deviation. Right here, this is sigma. This little guy that looks like sort of a circle with a circle wearing a hat. Sigma is the standard deviation of the whole population. The one right above it is the standard deviation of just a sample. And so we're not going to be using that. But see, when we did this, you've probably heard standard deviation a lot. And we talk about the fact that the standard deviation is a measure of spread. All right. But a lot of times that doesn't mean a lot to people. Other than, okay, yeah, it tells me how spread out the data is. So if it's bigger, it's more spread out. If it's smaller, it's less spread out. Well, now we get to look at the specifics of that. It turns out that on a normal distribution or the normal curve, the width of one of these sections is 1 standard deviation. So for instance, on the data I just showed you, standard deviation was like 8.4. From here, from the mean to this line would be 8.4. And then from this line to this line would be 8.4. And this line to this line would be 8.4. So the bigger the standard deviation is, the more spread out this is going to be. If I had a standard deviation that was bigger than 8.4, so assuming this one's 8.4, it's going to look more further spread out. If I have one that's smaller, that means these little areas get closer and closer to each other. So it's going to make my data a little bit closer to the middle. All right, I want to try and show you one that's sort of interactive here. So let's see if I can do this without it being really weird. But I'm going to Desmos. And here you see on Desmos a lovely normal distribution curve. And right now it's not centered on 0, 0. So I'm going to move it over just a hair. There we go. All right, so right now the mean is 0 because that's the middle of the curve. But I can move it to the right to where now the mean is about 2, or to the left where right now the mean is about -1. Another thing I can do is I can change the standard deviation and look at what happens when I change the standard deviations. Right now the standard deviation size is 1. Okay, so we have from here to here is 1 standard deviation, and then from 0 to 1 is another standard deviation. That's the width of a standard deviation. All right, if I make that larger, all right, we would expect, if this is going to spread out, we would expect the whole curve to spread out. And look at what happens. It kind of flattens it out. So when my standard deviations are bigger than 1, and as they get bigger, the curve sort of flattens out. That's a standard deviation of almost 2. Now let's go back to a standard deviation of 1 and see what happens if the curve, see what happens to the curve if my standard deviations get smaller. If those regions get narrower, it's getting higher and higher and higher to where you couldn't see it because it was 0. So this is a standard deviation of 0.3. And here's a standard deviation of 0.7, 0.9, 1.1, 1.4, and so on. So that's just a little bit of an idea of how changing the mean and how changing the standard deviation changes your curve. So a lot of times when we draw our normal distribution curve, we also say this is 1 standard deviation above the mean. This is 2 standard deviations above the mean. This is 3 standard deviations above the mean. We label it like that. And going to the left of the mean means this is 1 below the mean. So we consider that -1 standard deviation. -2 standard deviation, or 2 standard deviations below the mean. And -3 standard deviations below the mean. Okay, so for instance, let's just talk about what that would mean with an actual example. Let's suppose that I found the stats for a particular problem, and I found out that the mean was 50 and the standard deviation was 6. What that would mean, no pun intended, is that 50 is here, and that 6 above that is here, and 6 above that is here, and 6 above that is here. 6 below the mean is here, minus 6 again is here, and minus 6 again is here. All right. So that means I would expect most of my data to be near 50, and less of it would be out here in the upper 60s or in the lower 30s. Not much of it would be there. That would be a normally distributed set of data that has a mean of 50 and a standard deviation of 6. All right. So now let's talk about why this helps to know. I mean, what can I do with all of this? Well, one nice thing I can do is I know the following things. This is the empirical rule. The empirical rule talks about the normal curve, and it tells me that 68% of the data, 68% of my data, is going to be within one standard deviation of the mean. Okay, 68% is going to be within one standard deviation. Within means on either side. Okay, so because here's the mean, and here's one standard deviation above, and here's one standard deviation below. So 68% of the data is going to be from here to here. All right, now it's nice that it's symmetrical because that tells me that if I cut 68 in half, I should expect 34% of my data to be right here and another 34% of my data to be right there. Okay, so that's 68% of the data. Now the next thing that happens is it turns out that I expect, let's see, 95% of my data, which I'm going to put right here, is between -2 standard deviations, or 2 standard deviations below and 2 standard deviations above. So we say that 95% of your data is within 2 standard deviations of the mean. And finally, let's see where I can draw this. Excuse my computer. 99.7% of your data is within 3 standard deviations of your mean. So the vast majority of your data is within 3 standard deviations of the mean. Does that mean there can't be any data outside of that? No, not at all. Okay, but it does mean that most of your data is going to be within 3 standard deviations of your mean. So there is some outside of that. Let's look at this percentage-wise. If we had 68% here, 95 minus 68%, it turns out that about 13.5% of your data is going to be in each of those 2 sections. Okay, and then the next 2 sections, we say that about 2.35% of your data is in those 2 little sections, in each of those 2 little sections. And then finally, 0.15% of your data is bigger than that, and another 0.15% of your data is smaller than that. So that's less than 1%. So we're talking together, that's 0.3%, so significantly less than 1%. So whenever I'm told I have a normal distribution, these are the numbers I get to use. So let's go ahead and go back to our Chicago problem. If I can figure out where I put it, as I am throwing things around here. The Chicago problem said the high temperature in Chicago for the month of August is normally distributed with a mean of 80 degrees Fahrenheit and a standard deviation of 8 degrees. Okay, so that means I'm going to draw my normal curve, and it helps to have some spares already set up, which I thought I did. And I found them. And so I'm going to take that mean temperature, they told me that it's 80 degrees Fahrenheit, the mean is 80 degrees Fahrenheit, and say that means 80 goes right here. That's where my mean is. And my standard deviation is 8 degrees. So that means I'm going to go plus 8 to get here, plus 8 again to get here, and plus 8, 96, and plus 8 again to get here. All right, and then that means going to the left of my mean, I'm going to subtract 8 each time. So 80 minus 8 is 72. 72 minus 8 is 64. And 64 minus 8 is 56. Okay, what percent of days, now I'm ready to answer my questions. What percent of days in Chicago in August will have a high temperature above 90 degrees? And I say I'm ready, but I really need to go ahead and fill in those percents. So let's go ahead and do that. Remember, this was 34%. And again, these are the same every time. That's the beauty of normal curves, is if it's normally distributed, that means it always fits that shape. And that means those percentages are the percent of your area that's in that one section. So 34% each of these two places, 13.5 here and here, 2.35 in here. And you could potentially have to use that 0.15, but most of the time you're asked about the ones that are closer in, because most of the time, remember, the majority of your data is going to be within 3 standard deviations of the mean. So what percent of days in Chicago in August will have a high temperature above 96? Well, here we go. This is 2.35%. We said that this over here is just 0.15%. If you add 2.35 and 0.15, you get 2.5%. And that's my answer. So I'm looking here and I said 96. The ones above that would be to this side. So I just add up those two sections. Next we have what percent of days will have a high below 72 degrees. Okay, so here's 72 degrees. Below that would mean the 13.5% here, the 2.35% there, and the 0.15% there. Okay, so these two together is 2.5%. Add that to 13.5% and you get 16%. So 16% of the time, or of the days, you'll have a high below 72 degrees. Part C, what percent of days will have a high between 64 and 88 degrees? So 64 and 88 degrees, between there and there. Notice that all the questions are asking me about numbers that are right here. Okay, if you are asked a question about numbers that are not right there, the numbers that you found by doing 1 standard deviation and 2 standard deviations and 3 standard deviations, you're being asked to do something a little different, and that is use a z-score. That's going to be a separate video. Just keep in mind that if you're asked something other than about these numbers, you're probably going to need a z-score. So we were asked between 64 and 88. So let's shade if I can find a pencil. That means between here and here. So that means this section right in here. So 34 and 34 is 68. And add 13.5 to that, and I get 81.5, I believe. I'm doing it in my head. If I get it wrong, trust your calculator, not me. What is the probability that a randomly selected day will have a high temperature between 72 and 80? 72 is here, 80 is here, that's 34%. And that is how I answer my questions. Let's do another one, just for good measure. 2 companies market new batteries targeted at owners of personal music players. Duratunes claims a mean battery life of 11 hours, while Rock Ready advertises 12 hours. So that's the mean. Assume that the distributions of battery life are approximately normal. Suppose the standard deviations are 2 hours for Duratunes and 4 hours for Rock Ready. Okay, so Duratunes, we have a mean of 11 and standard deviation of 2. So Duratunes Mean of 11, standard deviation of 2 means 2 to get here, and 2 to get here, and 2 to get here, and 2 down, 2 down, 2 down. Okay? Now the other one said Rock Ready has a mean battery life of 12 hours. That's the right here. And that 4 hours is the standard deviation for Rock Ready. So 12 in the middle, and then plus 4, plus 4, plus 4 going to the right, and minus 4, minus 4, minus 4 going to the left. And that's Rock Ready. So we're being asked to compare these two. Now I would probably go ahead and fill in the percents. This is 13.5, and that could take a little while. So let me let you skip it. And hopefully you caught that in my rush to get this filled in, I started to write the wrong thing there. So I started to write 13.5 for both of those, or I did write them. And both of those should be 34%. Okay, so now we're ready to answer the questions about these distributions. So you are headed for 8 hours at the beach. Which battery is most likely to last all 8 hours? Okay, well, let's see. What percent of, let's look at what percent of Duratunes and what percent of Rock Ready is going to last 8 hours. It's easier to look for Rock Ready. We know that from here up, this percent is lasting more than 8 hours, which is what we want. Okay? One thing to keep in mind, if this is the mean, remember this is the middle, that's the mean, that's the average, then everything on one side of it is equal to what percent? It's perfectly symmetrical. Everything on one side of it is 50%. So this whole part over here is 50%. So I've got 50% of Rock Ready batteries are going to last more than 12 hours. So I'm going to count that 50%. And then another 34% is going to last between 8 and 12. So 50 plus 34% tells me that 84% of Rock Ready are going to last greater than 8 hours. Well, that sounds pretty good. But let's look at Duratunes. Well, 8 is not on there. But here's the thing. The same percent as below here, one standard deviation to the left and up, is going to actually last 9 hours. And 8 is somewhere in here. So if that was 84%, this is 84% right in here. And then we also have this extra part here. So Duratunes, I don't know what it's going to be, but I do know, and you could find that out with z-scores. That's that thing I said you might have to look at another video for. But I do know it's going to be bigger than 84%. So more than 84% of Duratunes will last more than 8 hours. So my answer is Duratunes. If your beach trip is all weekend, and you probably will have the music on for 16 hours, which battery is most likely to last? Okay, 16 hours. So let's find it on each of these. Here's 16 hours on Rock Ready. Here is 16 hours on Duratunes. Well, which one has a higher percentage above there? Because we want it to last at least that long or more. So that means to the right. Right here, we've got 13.5 plus 2.5, 16% of Rock Ready batteries are going to last more than 16 hours. This is clearly a smaller percent. This is less than 3% altogether. It's less than 2% altogether. Is going to last more than 16 hours. So for the second question, my answer is Rock Ready. I hope this helped. We will come back and look at some more examples. Actually, yeah, I want to stop here. There are some more things I want to talk about, but we will talk about them in another video. Thanks for watching.